Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very happy to have Al Roth here from Harvard on the move to Stanford, right, very soon, to talk here. And most of you probably know Al already, and Al has done tons of super important work on matching theory, so today he's going to talk about a project he's worked for a long time on kidney exchange, random graph models and kidney exchange. And just about questions, we follow the econ conventions today a little bit, so you can interrupt Al and ask questions if you don't if you want a clarification. And but if you have really long ones, maybe we'll leave them a little bit towards the end, before the reception.
Or after the reception.
After reception.
Yeah.
Yeah, we have a huge group going for dinner, and if you were excluded from that group, you can also talk to me after the talk.
Okay, well, so thank you. I'm glad to be here. I'm going to tell you about some work on kidney exchange. I'm going to have to, since not everyone knows what kidney exchange is, I'm going to have to start at the beginning and tell you a lot about what it is. But eventually I'll be talking about work I'm doing with David Gamarnik, who's here, and Itai Ashlagi. But I'll get there. And if there's time, we can talk about some other things as well. But let's see how quickly things go. Okay, so in general, I've been working in market design, as Marcus said, in lots of kinds of matching things. The part that I'm going to talk to you about today is about kidney exchange. But there are some things, before I begin, that are common to market design in general that will be helpful to think about as I tell you about kidney exchange. And for that, let's think about what marketplaces have to do in general, because kidney exchange is a marketplace. One thing a marketplace has to do is it has to make the market thick. It has to bring enough people who want to transact together so that they can transact with each other efficiently. And with kidney exchange, that's going to involve assembling appropriate databases of patients and donors that we can consider whether they can exchange. Once a market becomes thick, though, it sometimes becomes congested. That is, it's thick, there's lots of people, so there are lots of transactions to consider, lots of transactions to explore, and some aspects of those may take time and other resources. And so one thing you have to deal with in a thick market is how to deal with the congestion. And in kidney exchange in particular, the congestion is going to involve the resources that are needed to assemble large exchanges. And then marketplaces have to be safe to participate in. And that is, when you create a marketplace, you want it to be someplace that people will come to do their transactions in the marketplace and not do the transactions elsewhere because they may lose something by coming to the marketplace. And in kidney exchange, what's going to be important is as kidney exchange has developed, what we've seen is that large transplant centers are now starting to withhold some of their easy-to-match pairs and only showing the exchanges the difficult-to-match pairs. And that's a problem that has many causes, but one of the problems is that we don't yet make it safe for hospitals to show us their easy-to-match pairs. They could lose something by showing them to us, but it's very costly when they don't. And then the last thing that we see in many markets, but never as nowhere more clearly than in kidney exchange, is that some kinds of transactions are repugnant. So people have intuitions about economic ideas that sometimes elude economists who think that all sorts of voluntary transactions are okay. And I've been doing a lot of work. I was talking to Philadelphia Public Schools this morning about allocating school places, and they have opinions about what are right ways and wrong ways to do that. But in kidneys, the big repugnant transaction is in most of the world, it's illegal to buy or sell organs for transplant. Okay, so we don't use money in these markets. And one of the questions is, why not? And if there's time, I'll try to talk about that a bit. That's an interesting topic, but I just heard that the talk doesn't really go to 5:30, so I'm not sure that we're going to have time for that. Okay, so my plan is to tell you about kidney exchange, what it is, how we initially modeled it and how we initially helped kidney exchange get going in the United States, because that market has changed over time, and it's changed as kidney exchange has grown. One of the things about markets is they're sort of public goods. A well-working marketplace is a public good. Once you have a public good, you can start to have free riding. So at the beginning, the only kidney exchange going was the limited kidney exchange that we had in 2005. Now there's a lot of kidney exchange, and so the opportunity for hospitals to withhold their easy-to-match pairs and only show their hard-to-match pairs has emerged. And partly what's gone on is that hospitals have become players, and they have different strategy sets than patients and surgeons have, because hospitals see sets of patients, and so their strategy sets are different. So I'm going to show you a sort of an idealized model of large kidney exchange, which, when I say idealized, what I mostly mean is if we were seeing all the patients. And then I'm going to tell you about why it's not working that way. The fact that we're seeing patients being withheld, easy to match patients, gives us much harder to match patients. That makes the graphs, the connectivity that we're seeing, much sparser. And that's the recent work that David and Itai and I have been doing. And so I'll tell you about that. It turns out different kinds of exchanges work well in these highly sensitized, in these difficult to match patient pools that we're now seeing. So I'll tell you about that. And if there's time, we can talk about why do we don't just buy and sell kidneys. Incidentally, the one place where there's an entirely legal market for kidneys is the Islamic Republic of Iran. In most other places, it's illegal, although there are, and throughout the West, but there are certainly places where its legal status is unclear. But there are black markets and there are gray markets. It's hard to stamp out monetary markets, even in places where it's clearly illegal. So let me tell you about kidney exchange. And it starts with kidney disease. Kidney disease is a bad disease. It's a fatal disease, but end-stage renal failure. But there's kidney dialysis, which is to say there's a treatment that can keep you alive while you wait for a transplant, which is close to being a cure. And as a result, there are lots of people waiting. There are 90,000. And I don't remember. So yesterday, when I looked, there were 92,786. Let me just mention, to put things in context, I think I may have a slide that says this near the end, but let me say it at the beginning. I'm going to tell you a story of victory after victory of all the advances we've made. But when I started, there were 40,000 people waiting for kidneys, and now there are 90,000. Okay, so we're having victory after victory in a battle that we're losing. So maybe we can talk about that at the end, in a war that we're losing. So there are 90,000 patients waiting, and the reason there are 90,000 patients waiting is every year more patients are added to the list than are removed from the list. And you get removed from the list by having a transplant or by dying or some other ways, but the good way is to have a transplant. And in 2011, there were 11,000 transplants from deceased donors. But it's costly to wait, so 5,000 patients died while waiting, and another 2,000 were removed from the list as too sick to transplant. So these are guys who are not doing well. The waiting was very costly. But in addition to those 11,000 is way smaller than 90,000. That means that waiting list is very long. But a dead person, a cadaver, is not the only source of kidneys. Each of you has 2 kidneys, and if you're as healthy as you look, you can remain healthy with just 1 kidney. So if someone you loved had end-stage renal failure, you could give them a kidney, if you're healthy enough. If you don't have high blood pressure, if you don't have diabetes, if you don't have protein in your urine, you could give someone a kidney and be fully healthy afterward. Okay? So in 2011, there were 5,700 transplants of kidneys from living donors in the United States. Notice that means it's not obvious, it means we have more living donors than we have deceased donors. Right? Deceased donors give both their kidneys, living donors just give 1 kidney. So the modal donor in the United States is now a live donor. Okay? And you might be healthy enough to give a kidney to someone you love, but they might still not be able to take your kidney because there are reasons that you can be incompatible, I'll talk about these, with someone who wants to give you a kidney. And that's where the possibility of exchange opens up. So the simplest type of incompatibility is incompatible blood types. So here's donor 1 and recipient 1. Donor 1 loves recipient 1 and would like to give her a kidney, but donor 1 has blood type A and recipient 1 has blood type B, so she can't accept his kidney. They're an incompatible patient-donor pair. Okay? But here's another incompatible pair that has the reverse blood type. They can do an exchange. That's the double coincidence that makes the simple exchange possible. The A donor can give to the A recipient, and the B donor can give to the B recipient. So that's an exchange. And sometimes people say, why are economists involved in kidney exchange? And of course, who else studies exchange than economists? This is an old problem in exchange. Yeah?
On the previous slide, the numbers didn't quite add up, so just...
That's right. I haven't accounted for everyone here. Okay. That's right.
And you're going to tell us something? Or?
No, I'm probably not. The data aren't good.
I see. Okay.
That's one of the reasons. So there are people who, you move, not everyone is getting adequate care, so not everyone is on the list who should be. People are removed from the list because so there's lots of stuff going on. I am not going to talk about the people not there. The point I wanted to make from this is that there are not enough transplants. Yeah.
Do we have an estimate of the size of the black market, at least among...
Black market in the U.S. is pretty small. I don't have an estimate. There's a lively black market around the world. Mostly if you wanted to buy a kidney, if as an American you wish to buy a kidney, you would probably have to travel, although sometimes the seller donors travel.
And you might leave this list.
Those guys, no, if you bought that could be some of it, but if you bought a kidney in the United States and had a donor come, the donor would claim to have met you at church and love you, and you would be included as in the statistic. If you go elsewhere, you're not. That's right. Okay, Jevons talked about barter, right? This is, actually Jevons talked about money, and what he said was money is a market design solution to the thing that impedes barter transactions, which is you need a double coincidence, right? To have a barter transaction, you have to find a barter transaction occurs between two pairs such that, if you're one of the pairs, they have what you want and you have what they want. That's the double coincidence. Otherwise, you can't do a trade. So Jevons talks about houses, and he says, what's the chance that someone whose house you want wants your house, and you can do a swap? Money relieves the need to find the double coincidence. You can buy what you want from someone who has what you want, get money, and then later, at some different time, sell, the buy and the sell can be separated in time. I got them confused there. And that's why we use money. It's a medium of exchange. It simplifies finding the double coincidence. So why don't we use money? Well, here's the sentence from the National Organ Transplant Act of 1984 that says you can't use money. It says, it shall be unlawful for any person to knowingly acquire, receive, or otherwise transfer any human organ for valuable consideration for use in human transplantation. So the phrase valuable consideration caused us some difficulty. You might think that kidney exchange is valuable consideration. There's some exchange going on there. So we got an amendment to the 1984 NOTA, which says that the preceding sentence, that sentence doesn't apply with respect to what's politely called human organ paired donation. They didn't like the word exchange in this law because that seemed too much like valuable consideration. So it's clear that the law was meant to outlaw sales. That was its intent. Kidney exchange didn't exist in 1984. You'd think it would have been easy to get the amendment. It passed in 2007. We'd been doing kidney exchange for 3 years already. It went up 3 times in Congress. There was never any opposition, but the first 2 times it just didn't get passed before Congress session ended. Charlie Norwood was the representative congressman from Georgia who died of a transplant-related immune disease, small cell carcinoma, and his colleagues named the act after him and passed it. Finally, he was one of the sponsors. And it passed with no opposition, right? So there was never any opposition, but legislation is hard to pass. So when we talk about transaction costs and congestion, there are things that everyone wants, but they don't always happen immediately, and that's going to be some of the story about kidney exchange too. All right, so let me tell you about kidney exchange a little bit. I'm the man in the yellow gown staying out of the way. There's a kidney in that bucket. It comes not behind my back in this picture, but not this picture. There's another operating room, and the nephrectomy has just been done. That is, the kidney has just been removed from the donor, been just carried steps away, and it's going to be transplanted into this guy who's right there. And this is happening in Cincinnati, Ohio, maybe in 2005. At the same time, in Toledo, Ohio, his donor and her patient are having the same thing. And when I say at the same time, what I mean is in Cincinnati, the anesthesia was applied, the incisions were made, everything was ready to go. They got on their cell phones and they said, we're ready to go in Cincinnati. Are you ready to go in Toledo? And if something had happened in Toledo, some problem with the anesthesia or for whatever reason, the operations couldn't go ahead in Toledo, the plan was to sew everyone back up and not go ahead in Cincinnati. But everything was okay in Toledo, so they went ahead. So they do it simultaneously. And the reason is you can't give valuable consideration for organs, so you can't write a contract. You can't say, we'll do this today and you'll do that tomorrow in any enforceable way. And quite apart from enforceability, it could be that rarely, when a patient goes under anesthesia, something happens that makes the operation end. And so it might not go through, so they do it simultaneously. But what that means is that even that simplest exchange between just two pairs involves 4 operating rooms and 4 surgical teams. So it involves, this is the congestion that we're going to have to deal with. It involves a lot of resources. You have to assemble a lot of stuff at the same time to make a kidney exchange happen. Now, to do just a kidney donation, you need 2 surgical teams and operating rooms just to get the nephrectomy and small hospitals that don't have it sometimes do it with 1, but that's trickier. Then you're keeping the kidney in that bucket on ice longer. That's not so desirable, and there's still the chance that something will go wrong in preparing the patient for transplant. So what you'd like to do, even if you're doing not an exchange, just a simple donation, is you'd like to have 2 operating rooms and do them basically simultaneously. But we'd also like to consider longer exchanges. There'll be good reasons for this, and I'll tell you about them. And so, you could have a 3-way exchange. There's no reason you have to have that double coincidence. You'll find more exchanges if you don't need a double coincidence, right? If you have both 2-way exchanges and 3-way exchanges, more exchanges will be possible. But a 3-way exchange is going to be logistically complex because it'll involve 6 simultaneous surgical teams and operating rooms. And so, right, a 10-way exchange would involve 20 simultaneous surgeries. You can see that at some point they get too big to do. But when you have non-directed donors who don't have a particular intended recipient, you can also have chains, not just these closed cycles. There's a graph that David made. You've got this non-directed donor. You can, instead of just having 2-way cycles, here's a 2-way cycle, here's a 3-way exchange, you could also have some exchanges that could be long if we can figure out how to solve them logistically, how to do the logistics. So that's partly where I'm going today. So where I'm coming from, we originally wrote a paper that I won't tell you about, Taifun Sonmez and Riku Unruh and I, that looked at graphs like this. It looked at exchanges and chains and talked about integrating them together. Say again?
What do the colors of the edges mean?
Nothing at all. I took a graph that David made. They may have meant something in his talk, but right now the colors don't mean anything.
The darker ones are the
ones
exchanges
chosen.
that took place. The lighter ones, the exchanges that did not take place.
Okay, he's showing a maximal exchange. Okay, there you go. Thank you.
So when you have directed exchanges, is there still a reason for being simultaneous? The red person is giving anyway.
I'm going to talk a lot about that today. So that's an excellent question, by which I mean I have a number of slides designed to answer it. So we talked about integrating chains and cycles, but when we started talking to doctors, they said to us, this is in 2003, they said to us, we're never going to do more than 2-way exchanges. It needs 4 simultaneous operating rooms. If you want to help us out, tell us how to do 2-way exchanges. So I'll tell you a little about that. Eventually, we discovered that it was really too bad that you could only do 2-way exchanges, but if you could do 3-way exchanges, you'd get most of the benefit of being able to do large exchanges. So the New England Program for Kidney Exchange and others developed the logistics to do 3-way exchanges. Those are now pretty common. But as I started to indicate before, as kidney exchange started to succeed, the players and the strategy sets changed. When we started, the players were patients and their surgeons. So surgeons with individual patients. And nowadays, among the players are directors of transplant centers. And directors of transplant centers have different strategy sets because they see groups of patients and donors, and they can select which ones to enroll in kidney exchange and which ones to withhold. That has changed the game. I'll tell you about that and how the game now looks. And one of its consequences has been the patients we see are now harder to match because, at least at the present time, this is a fixable thing but hasn't been fixed yet, at least at the present time, we're disproportionately seeing hard to match patients. So I'll tell you about graph models, random graph models of how the world looks if we were seeing all the patients and how it looks when we're only seeing the hard to match patients. This is also play out in the medical literature, and our colleague lately in some of this is a surgeon, Mike Reese, who's the director of one of the very active kidney exchanges called the Alliance for Paired Donation. It also, yes?
So if you take like two random people, what is the probability of them being compatible?
Good question. So if I didn't know my blood type, unconditional, so I'm a random person, the chance that you could take my kidney is over 50%. It's almost 60%. But the chance that my wife can take my kidney is only about 30%. And that's because my wife and I are parents, and in the course of childbirth, her immune system may have become exposed to some of the proteins that our boys inherit from me. And if so, she may have preformed antibodies against those proteins. And if my kidney were to show up, her body would be prepared to attack it. So random people, you could take my kidney, probability 60%, my wife 30%. And then it varies a lot, conditional on knowing my blood type. And I'll tell you about blood types. Another big thing is 60% because you seem to be pretty healthy. If you the sicker you are, the harder it is to take someone's kidney. And in particular, if you get a living donor kidney transplant, which is the best kind, its half-life is about 20 years. So if you got one when you were young, you're going to need another one in the course of your life. When you get the second transplant, you will have already suffered graft versus host disease. Your body will have rejected the kidney that was transplanted, and you will now have antibodies to the whole vector of proteins that compose that kidney. So you will be a highly sensitized patient, the kind we're going to be talking about. So if you had already had a kidney transplant and need a second one, then the chance that you can take my kidney drops dramatically. Okay, so it depends on lots of things. But for two healthy members of the population, it's 60%, but healthy members of the population don't need kidneys. Okay, so Itai Ashlagi is one of my co-authors here. So just incidentally, the process of doing kidney exchange, we do the kind of paper I'm going to tell you about today, which is sort of a scientific paper. But then there's lots of persuasion and different kinds of evidence has to be brought to bear to convince surgeons to do things. So all these things in the New England Journal of Medicine and the American Journal of Transplantation, these are a very different scientific culture. It's very interesting to deal simultaneously with both. And there's also a growing computer science literature that deals with some of the algorithmic aspects of this and some of the complexity aspects. Okay, so let me take you back to 2002 and 2003 when we were trying to get the New England program for kidney exchange started. And they said to us, we had this great plan for how to integrate chains and cycles, and they said to us, just two-way exchanges. That's all we're going to do. If you want to help us figure out how to do two-way exchanges. So this turns out to tap into some old and elegant graph theory. They also, in those days, thought that they were just going to have 0-1 preferences on compatibility. That's an exaggeration too, it turns out. But we said, fine, two-way. You won't get as many exchanges, but if that's all you can do, let's see what we can do. And the graph theory that's involved involves matroids, which are algebraic generalizations of the idea of a set of linearly independent vectors. So if you look at a matching, which you've got vertices and edges, and as long as we're talking about just two-way exchanges, I can treat the edges as undirected because only a double coincidence counts as an edge. Then you can look at the set of patient-donor pairs, the set of nodes, the set of vertices that can be matched, and they constitute what look like the independent sets in a set of linearly independent vectors. And that means, they're a matroid, that means it has the property that if you have a set of matched people, any subset is also matchable, also an independent set, any subset is independent. And if you have two independent sets, two sets of matchable people of different sizes, there's always a way to augment the smaller one by adding an element of the larger one and still having an independent set. So that makes it pretty easy to get incentive-compatible algorithms for matching, because you can use greedy algorithms. If you've got priorities on your patients, which is often how we think of patients when we're allocating deceased donors, you can just start with the highest priority patient and see if there's a match that gets that patient matched, and then you say, given that he's going to be matched, maybe to someone different than we think now, can we put in the second highest priority patient? And matching the highest priority patient may preclude matching the second highest priority patient, but it won't preclude matching two other matchable patients. So all the maximal sets will have the same size, and you get good incentive properties. You need incentive properties. When you think about incentives, discussing incentives with non-economists is sometimes a little odd. It was especially odd discussing it with surgeons, because they would start off denying that there were incentive issues, because they'd say, people don't have choices about whether to become sick. This is a desperate disease. There are no incentive issues. But as soon as you start talking to them, they understand immediately, because there are so many incentive issues in transplantation, and because everyone games them so heavily that you just, it just took an issue of explaining to them how, for instance, in deceased donor allocation, often the health status of the patient determines where he is on the line. It depends on the organ, where he is in the queue. So of course, hospitals had incentives to make their patients seem sicker than they were, things like that. The one I like to talk about here has to do with available donors. There's information that is, by its nature, completely decentralized and private. Supposing you need a kidney. So you go home for Thanksgiving and you say to your family, I need a kidney, and your brother and your sister are both willing. We're only going to know about your brother and your sister if you tell us about them. If we had some system that, for instance, it would be a bad system. Supposing we gave priority to people who only had a single donor because they're less lucky than people who have two donors. Well, everyone would only have a single donor, right? But having multiple donors makes that graph much denser, because although only one of your donors will actually give a kidney, you're connected with other pairs through the double coincidences of either your brother or your sister. One pair might be able to give you a kidney and take your brother's kidney, and the other one might be able to give you a kidney and take your sister's kidney. So it's obviously important to have as many connections as possible, and this kind of matroid greedy algorithm makes it a dominant strategy for everyone to reveal all those connections. So from graph theory, without anything about kidneys in it, we can tell you something about maximal exchanges. And in particular, the thing we can tell you, there's a theorem called the Galai-Edmonds decomposition theorem. The thing we can tell you is that there'll be some under-demanded nodes. These are nodes that are matched at some maximal matchings, but not at every maximal matching. And there'll be some over-demanded nodes. These are nodes that are neighbors to those who are to the under-demanded nodes, and it's their allocation that determines which under-demanded nodes are matched. So there's also some perfectly matched nodes that are matched at every maximal matching. So what I'm going to do now is populate these nodes for you, because we know a lot about who can match to whom in terms of blood types and things like that. So I'm going to tell you who's over-demanded and who's under-demanded, first in the perfect world where we're seeing all the patients, and then later in the world that we're actually seeing, or that we've come to see. This world wasn't a bad approximation of what we were seeing when we started kidney exchange. Okay, so what are the factors that determine who can take whose kidney? The first is blood type. You can take a kidney from someone who has the same blood type that you do. So if you have blood type A, you can take a blood type A kidney. But basically, there are these two proteins, A and B, and so there are four blood types. If you have one of them, you're A, if it's A. If you have the other one, you're B. If you have both of them, you're AB. And if you have neither of them, you're O. In many languages, that O, blood type O, is blood type 0. It means you don't have any of the blood proteins. And the rule is you can't take a kidney from someone who has a blood protein that you don't have. So everyone can take a kidney from a 0, an O donor, but an A patient can only take a kidney from an A donor or an O donor. An AB patient can take a kidney from everyone. Okay, so it's a transitive relation. Now, that's one type of, a big type of compatibility. That would be the dominant thing if we were seeing all the patients. Notice that type O patients are going to be at a disadvantage because they can only take O kidneys. And O kidneys are going to be in short supply, not because they're in short supply in the population. They're actually 48% of the American population, but because most of the simplest kind of withholding of easy-to-match pairs is withholding of compatible pairs. And that's a complicated story that I won't get into today, but loosely speaking, if you have kidney failure and someone you love wants to give you a kidney, and they can, they're healthy enough to give a kidney and they're compatible with you, most American hospitals will not tell you anything about kidney exchange. And you'll just get your donor's kidney. And as a result, we're only rarely going to see O donors because we're only seeing incompatible patient-donor pairs. And O donors are never incompatible for reasons of blood type. O donors can give to everyone. So why do we see any O donors at all? That's because of how sensitized you are, your antibodies. I already spoke about that in answer to the question of why my wife might not be able to take my kidney. She might have very few antibodies, but there's a chance that the antibodies she has are to me because we're parents. And so she might be a low sensitivity patient. The percentage reactive antibodies she has won't be too high. That's a number that when we look at patient statistics, it's a number that tells you what's the chance that you can't take a kidney from someone even though they're blood type compatible. So her PRA might be 10%. Bad luck. All her antibodies are to my proteins, but she could take one of your kidneys with no trouble. In a room this size, there'd be someone she could give it to. But there are some people who have had a transplant before. They've had a lot of blood transfusions. They've been exposed to a lot of human proteins. Their immune system has built up antibodies to a lot of human proteins, and they are highly sensitized. So for the purposes of this talk, I'm going to say a patient is highly sensitized if their PRA, the chance that they can't take a kidney from someone who, even though that someone is blood type compatible, is over 80%. Yeah?
This PRA is sort of a continuous variable, right?
It's a continuous variable. Right. Today I'm going to have high and low in my model, but it's a continuous variable, and I'll show you some of the measure that. It's definitely a continuous variable.
Okay, so they might do a transplant, but actually it might not live as long as it could because it
No. The question is what in a pool of this size, what's the chance you can find a kidney? That's what your PRA measures, and it's a continuous variable. But if you have antibodies to my kidneys, you have to take heroic measures to give you my kidney. So it's not so you can turn it into 0-1 ex post on any individual pair. There are in Japan where they don't have much deceased donation, they do a lot of what's called plasmapheresis. You can take out all your blood and scrub it of antibodies, and you can do heroic things, but that makes the success work much less well. So it's good to get a compatible kidney. So there's lots of O's in the population, but not in the in the incompatible patient-donor pair pool. And when we look at PRA, only about 10% of the people have over 80% PRA. So high PRA patients are rare in the patient distribution. This is in the 90,000 people waiting for kidneys right now. Okay, so let's think about a model of random graphs, because we've got this PRA, which gives you random links. Let's think about models of random graphs where we can ask what would efficient matches look like if in the ideal case that the kidney exchange population looked like the general population. And then we're going to see that there are some incentives for hospitals to withhold. The question is, how costly would it be to remove those incentives? How costly would it be to promise hospitals that if they showed us all their pairs, we would make sure that they got to do as many transplants as they could have done any other way by withholding some of the pairs? Okay, so we're going to have a random compatibility graph where there are, at any moment, n patient-donor pairs that will generate from population statistics that if we generate a compatible pair, we won't enter them into the pool. We'll send them out, and then we'll generate the edges according to the blood type compatibility and the PRA. And this allows us to tap into some elegant graph theory for random graphs. There's the Erdős-Rényi family of theorems. And what it says is let's look at the probability that one node can take a kidney from another node. If that doesn't fall too fast, then we're going to get a giant connected component that perfect matchings are going to exist. If the probability doesn't fall too fast, if the probability basically stays high enough so that the room gets bigger and bigger and there are more and more people in the room, chances are you can take a kidney from one of those people as n goes to infinity. Okay, and so we'll get a perfect match, which will mean that all of the under-demanded pairs get matched. And the only ones left over are the over-demanded. Sorry, I said that backwards. All the over-demanded pairs will get matched. The only ones that get left over will be under-demanded. So let me show you which ones those are and what an efficient match would look like. So this is a theorem that Itai Ashlagi and I proved. And all the guys in gray are over-demanded. There aren't going to be any of these left over. Remember the Galai-Edmonds decomposition. They were under-demanded and over-demanded. So now we can look at who's over-demanded. Who's over-demanded is patient-donor pairs where the donor is blood type O. Or patient-donor pairs where the patient is, let's see, let me make sure I'm in the right direction. So these are patient donors. So if the donors are O, they're in short supply. They can go anywhere. And also over-demanded are the ones where the donors are pretty easy, not too hard to get rid of, but the patients are really easy. They can take from anyone. And the under-demanded pairs, the pairs that are going to be left over after we've done a perfect matching, after we've matched everyone we can match, are going to be the O patients with the A donors. That is, the patients who can only take an O kidney, but they're only offering an A kidney. Things like that. Yeah?
If you don't remove the pairs that are compatible with each other, then
Yeah.
how would this graph look?
Well, we'll have a lot more O. I think it wouldn't change a whole lot, but there'd be a lot more of these.
So we would still have under-demanded pairs?
Yes, I mean, it's still the case that an O kidney can go into anyone, but an O patient can only take an O kidney. So the demand for O kidneys will be higher than the supply. Right? By and large, if you got everyone, then you'd have the same number of O kidneys and O patients, roughly. But anyone can take an O kidney.
But we cannot do like a perfect matching on that graph? Because,
I'm sorry?
I mean, if we have this and also we have those compatible pairs, this is like a suboptimal solution to the whole problem, yes?
Putting in compatible pairs would help a whole lot. I mean, so we've written some papers on this. Yeah, it would help a whole lot. The reason I'm having trouble answering the question is you're going to see that this isn't the way we're currently doing the matches because of the high sensitivity issue, and that actually changes things quite a bit. It turns out highly sensitized patients have O donors, right? I mean, if you have an O donor, but you are incompatible even with your O donor, the ex post probability of you being highly sensitized has gone way up. So in fact, although in this idealized world we're done, there are no more O donors. In fact, there still are O donors. They're paired with highly sensitized patients. So I'll sort of get to that. So it turns out what an efficient match would look like. Efficient matching, if we were looking at all this, is we wouldn't need really big matchings. We wouldn't need 10-way exchanges. The biggest we'd need is 3-way exchanges. What's going on here is you say, look, we've got around the same number of patient-donor pairs that are blood type B and A, and those that are blood type A and B. But in any realization, there'll be more of one than of others, supposing there are more ABs. So we match all the BAs to AB pairs, right, in that simple 2-way exchange. And now we've got these ABs left over, and what we can do with them is we can have the the B donor give to the B patient here, the O donor here give to the O patient here, and the A donor here give to the A patient here. So that's a 3-way. Here's another 3-way. But mostly because we've got this giant connected component and this big shortage of over-demanded pairs, this stands in for all XX is both patient and donor have the same blood type. So AA, BB, OO, AB, AB. And they're sort of perfectly matched in the big world. So this is what it would look like. The over-demanded pairs are all matched, and you don't have to do big exchanges. Okay, that's the ideal world. Let me tell you about the world we're seeing. Incidentally, we never saw the ideal world. In the early days of kidney exchange, this was the kind of graph we were getting, but we didn't have very large numbers. Now we're getting somewhat larger numbers, but we're not getting these patients. Okay, so we're seeing some hospitals withhold internal matches. And this was actually something that we knew about at the beginning, but we couldn't get our colleagues to adopt incentive-compatible things for hospitals, right? Because there's a culture of saying we're only going to consider, in considering who gets which kidney, we're only going to consider medical criteria, not what hospital you came from. And that turns out to be a tough one, because what hospital you came from is what motivates the transplant center directors to decide which patients to put in or not. They're concerned with getting enough transplants. Okay, so I want to say, how costly would it be to promise hospitals that if you show us all your patients, we will make sure you get as many transplants as you would have gotten if you'd showed us a subset? And in the worst case, it's very costly, but in the average case, it costs almost nothing. And so there are mechanisms we could do that would fix this. Let me show you the worst case and then explain the average case. So the worst case, it says, supposing there's some maximum size cycle exchange you can do. Supposing it's 3, which is a good, I mean, we see occasional 4-way exchanges, but mostly we top out at 3-way exchange. Then it could cost up to 1 over k minus 1. It could cost half of the number of transplants to guarantee individual rationality. Okay, why is that? Well, let's look at hospital A. It has these 3 pairs, A1, A2, A3, and it can match them internally. It's a big transplant center. It's in Boston, say. It could match them internally, and it would get 3 transplants. Or it could show them to the kidney exchange, in which case the whole compatibility graph will look like this. And what the kidney exchange is going to want to do is get 6 transplants by matching A1 in a 3-way exchange with pairs E and C, and matching A2 in a 3-way exchange with B and D. So that's, of course, not so good for Hospital 1, which only gets 2 transplants in that case, and regrets that it showed all 3 of its pairs to the kidney exchange. So it could be that to say to Hospital A, we're going to guarantee you getting your own, it could be that that would mean we had to do half as many transplants as it would look like we could do if we had the whole graph. Of course, even in that case, you have to figure that if you're not seeing those A pairs, then you can't do any transplants anyway. Okay? But and this can, and you can worry about this even with just 2-way exchanges, right? It's not because of 3-way exchanges. Here's Hospital A again. It can do a 2-way transplant between A1 and A2, but if they show us everything, we'll do a transplant, an exchange between A1 and B and A2 and C, and that'll allow 4 transplants instead of just 2. And 4 transplants would be just fine for Hospital A. I'm sorry, they would still get their 2 transplants from those 4. But what they're worried about is this case, that when they show us their patients, we don't have a B and a C, we just have a B. And maybe B is a high priority candidate, maybe B is a child. And so right now what we're inclined to do is we say, well, we found a great exchange, we saved the child. But Hospital A doesn't feel so good about that. And the difficult discussion with our physician colleagues, that this is one, we've won lots of arguments, but we haven't won this one yet, is to say, you have to give priority to A1 and A2 in this case. You have to promise Hospital A that you're going to transplant their patients. And they say, and leave the child without a kidney. And you say, the child is not getting a kidney. You're not seeing A1 and A2 nowadays. So if you don't promise to transplant A1 and A2, who are perfectly ordinary, middle class, unremarkable, not terribly sick patients, so no medical reason why they should take priority over the exchange A1 and B. If you don't promise that they're going to take priority, you're not going to see them. So this is one of the things we haven't yet won.
What are the current rules for priority?
They're different in each kidney exchange. There are elaborate rules that have the status of sort of federal regulations about priority for deceased donor organs, because we think of deceased organs as being sort of a national resource. But living donor organs are, right, you completely control your organ, and so there are no national rules about that. Right? Your living donor organs, you guys have complete control. You're using them as we speak, and you have all the rights over them. So there's an absence of, so each of the kidney exchange we worked with has some ideas about priorities, but in the end, they come up with a match, they propose it to the transplant centers, which can say yes or no. And of course, the donors can say yes or no. And the patients can say yes or no, right? So unlike deceased donors who have much smaller strategy sets, everybody here has a large strategy set, so there are no hard and fast regulations. Instead, there are market design rules in each kidney exchange.
So if this full information revelation leads to some hospitals losing some patient transplant, can one convince the patient of B to move or enroll in A1 so that they don't lose the
yes. So that's in fact the business model of some of the bad actors, right? So there was a time when very few transplant centers in the United States could do transplants. Very few hospitals were transplant centers. And in those days, if you needed a transplant, you moved to Pittsburgh or to Baltimore or to Boston or to San Francisco, and those hospitals did all the business. Nowadays, there are 250 transplant centers that can do kidney transplants, and so multi-hospital kidney exchange is a very realistic thing. But when you look at the politics of this, some of it's driven by people who say, we're Hospital A, you should come to Hospital A. Why should, come to Baltimore? Yeah.
Could you give some intertemporal, things like, for example, if you give up a transplant today, we're going to give you some preference tomorrow to make that somehow?
I think you could. I'll talk a little about that. There's always the question of does it violate the National Organ Transplant Act restriction on valuable consideration, but we think we can do it under the radar, and I'll tell you about that. Yeah.
So in the absence of getting these hospitals to agree to full revelation, do you just assume that they create the biggest graph they can within their own network and then give everyone else the...
Yes, when I tell you what are the costs of having them withhold, that's what I'll assume, that you hope they do optimally internal exchanges, and then they show us the rest.
I have a question. Why don't, is it a privacy issue? So why isn't, one would expect that there would be some kind of Craigslist for this.
Some kind of?
Craigslist.
Craigslist. There are starting to be a little bit. There are websites you can sign up at, but it turns out mostly you get advice from your surgeon, right? So you have this debilitating disease, you have had it for years, if you weren't satisfied with your surgeon, with your doctors, you went to another one. Now you are dealing with a surgeon, your disease has progressed, and it turns out to be hard. You're not feeling that well. There are people who enroll in multiple exchanges. There are hospitals who enroll their patients in multiple exchanges. And there are hospitals that don't enroll in exchanges at all.
It seems to me like the patient, his incentive is to tell all the world, I need help, we need help. We're to
So that's part, so there's two places where that comes. One is finding a donor, and the other is finding an exchange. But if you go to Hospital A, they say to you, we're going to try to match you internally. We think that'll be simplest, it has easy logistics, we think that would be best for you. If we can't match you internally, we'll enroll you in exchange. Now, that free rides on the public good, so fewer general exchanges are done, but it might not be worse for you, right? Supposing you are A2, right? You say, I'm glad I'm in Hospital A, which is withholding its patients, right? So it's not clear that it's bad for the hospitals, and it's not clear that it's bad for the patients, for some patients, right? So the question is how to help everyone. There's room to help everyone because it's far from the Pareto surface. So if we can lift it up to the Pareto surface, we can give something back to the hospitals to make it a Pareto improvement. And indeed, we have a proposal for that. Let me not tell you why only three-way exchanges. Part of the story is, actually, let me tell you. One thing we worry about is this inefficiency. Here they're doing this little exchange when we could have done something, more elaborate. We also worry about heroic, news-making efforts. Here's a four-way exchange, which is really hard to arrange at your hospital. But it's also wasteful. It's wasteful because it uses two over-demanded pairs, the ABO pair and the AB pair, and they could have each been used in two disjoint three-way exchanges. So we could have gotten 6 transplants instead of 4. So it's not just the hospitals that are withholding are sometimes the fanciest hospitals. And they like to do fancy things for their patients. But this 4-way exchange is a bad idea because it replaces 2 3-way exchanges. Okay, but it turns out, although the worst case is 50%, the amount you would actually lose is about 1.5%. And that is, you can design an algorithm that says we will guarantee each hospital as many transplants as it could get on its own, and we'll still get to do almost as many transplants as we would given that graph if we didn't guarantee it. And the reason is there are all those leftover O patients, right? So everybody has O patients with A donors that don't get matched. So a lot of tie breaking has to be done. You have to allocate the scarce, over-demanded O donors. And so this is where you can start to do what Marcus suggested, which is give you credits for showing us easy to match, low sensitized pairs. You say the more you show us of those, the more we'll break ties in your direction when there are going to be lots of optimal size matches that give the O kidneys to different O patients. We'll give them to your hospital's O patients if you show us all your pairs, if you show us lots of easy-to-match pairs. So I'm not going to go into the details of that, but it's possible to design a system like that would make it individually rational, and you can get it to be a truth-telling equilibrium for hospitals to show all their pairs. Now, just incidentally, so here's simulations with clinical data. You lose very few patients when you do individually rational as compared to efficient when you're doing three-way exchanges, right? We're really talking about losing one patient on average when you're dealing with 20 hospitals. But the cost, so while the costs of, if you get all the patients and then you promise the hospitals as many transplants as they could do on their own, the costs are very small. But the costs are huge if you think that what the hospitals are doing is optimizing internally and just going internal. Then instead of getting 161 or 160, you're getting 56. So having hospitals withhold is very costly. And it's very costly because the marketplace isn't as thick as it could be. The easy-to-match patients, I'll tell you more about this in a minute, the easy-to-match patients make it a lot easier to match the hard-to-match patients. Okay, and that's where our next paper comes in. Incidentally, there are other strategies that hospitals can employ. They don't have to just withhold internal pairs. They can withhold O donors, show all their O patients to the exchange. Some of the O patients will come back unmatched, and they can ex post match them internally. Okay, but a sort of a frequent flyer program that said if you show us a lot of easy-to-match pairs, we'll match a lot of your O donors, can be constructed that get you, very close to efficient mechanisms with truth-telling equilibria. But let me tell you a little bit more about exchanges as we're doing them. Every now and more, there are non-directed donors. When non-directed donors used to come in, they would be told, well, first of all, they used to be very much discouraged. Obviously, you have to go through a medical exam before you can become a donor. Part of that medical exam is a psychological exam. Giving a kidney does not cure clinical depression, for instance. So if that was your motivation for giving a kidney, you'd be rejected. But 10 years ago, lots of the examining psychiatrists thought that wanting to give a kidney was a sign of that something was wrong with you. So it was very hard to give a kidney. But when you pass through all the screens, what you'd be told is, great, you can give a kidney to some patient who is on the deceased donor waiting list. And typically you'd give to someone who'd been waiting a long time, someone who is at the head of the queue. But nowadays, we have this pool. So your gift would save a life. It would give someone a transplant. Now, though, we have this pool of patient-donor pairs waiting around. So now we can say to a non-directed donor, we can say, you could give to a patient-donor pair. The donor in that pair will give to another patient-donor pair, and the donor in that pair will give to a person on the deceased donor waiting list. So more transplants will happen. More lives will be saved because of your gift. And this is what this is what it looks like not in the graph. There are 6 people in this picture. And the question, this was an exchange we did here in New England, in the New England program for kidney exchange. And the question is, why are there only 6 people in this picture? And the answer is, because we could assemble, we convinced our surgical colleagues it would be worthwhile to solve the logistical problem of assembling 6 simultaneous operating rooms and surgical teams so you could do 3-way exchanges. And 6 is the number of people here, 3 donors and 3 recipients, 3 nephrectomies and 3 transplants. But now there's the question of if you're having non-directed donors, maybe you don't have to do them simultaneously. So let's think again why we do exchanges simultaneously and why maybe we could consider not doing them simultaneously. And this is something that we actually wrote in a surgical journal, American Journal of Transplantation. But it's a simple cost-benefit analysis argument that says the following. It says, look on the left at a standard two-way exchange. So why do we always do those simultaneously? Supposing we didn't. Supposing the plan was that on Monday, donor 2 would donate to recipient 1, and on Tuesday, donor 1 would donate to recipient 2. Supposing we were planning to do it non-simultaneously. And on Monday, everything works as planned, and donor 2 donates, and so that big X indicates he doesn't have a kidney anymore. And on day 2, something goes wrong, either incentives or anesthesia or, something happens, and donor 1 fails to donate to recipient 2. Well, that's a tragedy. The pair 2, donor 2 and recipient 2, they've been really harmed. They had a kidney surgery that didn't benefit them and that they didn't need, and they no longer have a kidney to exchange. They can't take part in next month's exchange. They've been really, really harmed, and that's why we always do these simultaneously. But now let's suppose a living non-directed donor shows up, and we're going to do it on Monday and Tuesday. Yeah.
Okay, but what if you do it simultaneously? So you can do it simultaneously, but even simultaneously something can go wrong, and then you put back the kidney and
No. If it goes wrong, it goes wrong. Even a live donor, right? If your brother wants to give you a kidney, it might not work.
Right. Okay.
So that's not good. But I mean it's a small probability, but some kidneys never work. And some kidneys fail after 6 months. Right? So no, everyone takes the risk. This is just to get rid of the incentive risk. Okay? So now let's think of this living donor. He comes along, and on day 1, he donates to recipient 1, like there. And on day 2, for whatever happened here, the same thing happens here, and donor 1 doesn't donate to recipient 2. So recipient 2 is very disappointed, but no tragedy has taken place because donor 2 hasn't given a kidney yet. They were scheduled to get a kidney before they'd given one. They haven't gotten it, but they're no worse off than before this live non-directed donor showed up. They can take part in next month's kidney exchange. They're still in business. They are, they're disappointed, but they're not harmed. So the cost of a broken link is much less when you have a living non-directed donor.
Maybe they are actually, because maybe next month's R2 was supposed to get from D1.
No, so they're somewhat worse off, but the cost is less.
Yeah.
And since the cost is less, we can start considering whether the benefit might be commensurate with the cost. And the first non-simultaneous chain was reported in this paper that, Mike Reese is the hero of this. He's the director of the Alliance for Paired Donation, but, a bunch of computer scientists and some economists are co-authors in this paper. And the first exchange at the time that we reported it had 20 people in it, 20 surgeries, 10 transplants. The last person on the chain, we wouldn't do this anymore, but was a lady named Helena McKinney. She was blood type AB. So blood type AB is going to be hard to find her a match. We try not to end chains now, a little more thought. Try not to end chains with blood type AB anymore because, remember, AB patients can take anybody's kidney. So most of them are compatible with their original donors. And the ones who can't, even though they can take anyone's kidney, they're really highly sensitized, so they're not compatible with her. Right? So it took a long time. 2 years later, found her a match. She gave a kidney. That chain is still going. This is what they look like in Parade magazine. There's Helena McKinney. So the question is, why are these non-simultaneous extended altruistic donor chains so effective? Mike Reese originally wanted to use the same acronym and call them never-ending altruistic donor chains, but and maybe he had something there. So why are they so effective? And so what's the question here? You can look at that long chain and say, that's a splashy public relations effort by a kidney exchange network. Probably all those people could have gotten exchanges in two-way exchanges or 2- and 3-way exchanges. And that's not a crazy hypothesis, but it turns out to be very wrong. So let me explain to you why it's not a crazy hypothesis and why it's very wrong. So remember this picture. In the ideal world where we're seeing all the patients we want, this is what exchanges look like. Supposing we go through and we do an efficient set of exchanges without the non-directed donor. So we exhaust everyone who's shaded. There are no more O blood type donors anywhere in the picture because all these shaded guys are transplanted. They're gone. Okay? And now a non-directed donor comes along, and let's make our lives easy by having the non-directed donor's blood type be O, so he can give to anybody. Let's see how many patients he can save. Well, this O donor can give to this O patient, who has an A donor, who could give to this A patient, who has an AB donor who can only give to an AB patient. The AB patients in the pool are all gone. There's always one on the deceased donor list. So there we are, 1, 2, 3, 6 people in the picture. And if you do a longer chain than that, it looks like you just must have been in here using guys who could have been used elsewhere. Okay, so that's the principled reason to suspect that maybe chains are just showy but are not getting anything extra. Okay, but there's a big disconnect between the model and the data, because this model says that at first order only blood type is important, and none of this sensitivity is important. It turns out, let me now explain to you why the sensitivity, the antibodies, are first order important, and therefore this isn't the right picture. Okay, so in the patient population, only 10% of the patients are high PRA. But in the Alliance for Paired Donation, and also in a bunch of other kidney exchange networks with which we're dealing, the percentage of patients with high PRA is 50, 65, 60. Okay, it's much, much higher than 10%. And when we look, say, just at the XX pairs, patient-donor pairs with the same blood type, we see the percentage of high PRA patients is much higher, and sometimes the average PRA for the high PRA patients is really high, right? So here we've got a pool of patients where a pool of high PRA patients where 69% of them are high PRA, and their average PRA is 99.5%. That means these guys can't take anybody's kidney. Okay? Their compatibility graph is not going to have a giant connected component. It's going to be a very sparse graph. And so what we need to do is find tools that will allow us to study what efficient exchanges look like and chains in very sparse graphs. And incidentally, when you look at the clinical data, having long chains really increases the number of transplants. So when we look at the data, we are not at all seeing this picture. We're seeing a picture where you get a lot more transplants by including long non-directed donor chains. So the question is, what's going on there? Here's a graph of AA patients from the network that Mike Reese directs. Okay, so what you can see here is these AA patients. There's 38 pairs. 30 of them are high PRA. The blue lines are the only cycles, the dashed blue lines. So there are hardly any cycles if you can just do these. And the cycles are almost entirely among these patients with lots of incoming arrows, among the patients who aren't highly sensitized, right? So all these highly sensitized patients, they are parts of chains that don't close. So the way I like to think of this is if you grab the blue nodes, the low sensitized patients in your hand, and you pick them up and shake them, you get this jellyfish. And the top of the jellyfish has a connected component. That's the low sensitized patients. And hanging down are those chains of highly sensitized patients. Because they're highly sensitized, the chance that they form a small cycle in particular is very small, because if everyone's highly sensitized in the room, the chance that I can give one of you a kidney is small, but maybe there's one of you to whom I can give a kidney. But the chance that you can give a kidney back to my highly sensitized patients is very small, because she can only take very few kidneys. But you could give a kidney to someone else if we're in a big room, and they could give a kidney to someone else, and they could give a kidney to someone else. So we're building chains, and eventually we could build giant cycles, but you can't do giant cycles. But non-simultaneously, you can do big chains. So here's the graph that Itai and David and I now look at. We consider graphs that have low sensitivity patients and high sensitivity patients. And low sensitivity patients, we're going to use the standard Urosh-Reni kind of model where there's a constant probability that you can take my kidney, and as you can take anyone's kidney, and that as the graph grows, you'll surely get a kidney that's compatible. And then we want to look at guys who will be hard to match even in a big graph. And we consider more degrees of sparsity than I'm going to talk about today, but in the paper. But let me look at the simple case where the probability will decrease as a function of n by a constant over n. What that means is, supposing you're a patient so highly sensitized that we expect to find about, in some pretty big pool, about 4 kidneys that you could take. Now, as we let n go up, we're going to keep that 4 as a constant. We're going to say, let's look at big graphs in which there are some people who can only take 4 kidneys from anyone in the pool. Okay? And those are going to be guys who, as the graph grows large, they're not going to be in a giant connected set at all. They're going to be in sparsely connected set that has very few small cycles. Now, notice, for the purpose of my talk, that a non-directed donor, that we actually do this when we're doing the matching algorithms as well, can be modeled as a donor with a patient to whom anyone can donate. So when I look at a long cycle, we can't do long cycles because you need too many operating rooms, but we can do long chains nowadays. So if a non-directed donor is in the cycle, you don't really have to come back to him, right? That's a virtual patient who comes with a non-directed donor. So I'm now going to tell you about long cycles, but I'll be telling you about chains when I tell you about long cycles.
How many of these non-directed donors are there?
There have been a couple of hundred in our experience now. So they're going.
People who are just nice, people who want to do good to the world.
Yeah, so originally many of them had a religious motivation. So the numbers have been going up. And every time there's a picture in the New York Times like this, more people come up, right? So here's a chain that had 60 people in it, 30 exchanges. So think of being altruistic as having a cost and a benefit. And part of the thing that these long chains do is they make the benefit bigger, and that brings out more people. Also, the medical community has gotten more used to the idea that you could be a healthy person who wants to give a kidney.
Do kidneys from cadaver be considered non-directed?
They can be, and it would be nice in many ways to do that, but there are 2 reasons why we don't. One of them is that there's a elaborate national bureaucracy about deceased donor kidneys, so it's hard to intersect with that in any easy way. But we actually have a variance in New England. For the New England Program for Kidney Exchange, we were able to use cadaver donors, but that's a complicated story. But the other is deceased donor kidney isn't nearly as good for you, right? So you'd much prefer to have a live donor kidney. So the only times when these come up are either when it's a perfect match or when someone's need becomes desperate. So sometimes you're in the pool, you're waiting, and then you can't wait anymore. So now you need a deceased donor kidney, but we can cause a chain with you getting it.
Presumably, if you could buy kidneys, there would be lots of these guys.
Right, everyone has 2.
So how many people are dying as a result of that?
That's a good question. Lots of people die of kidney disease. There are 90,000 people on the waiting list. There are 400,000 people on dialysis. So many of them, some of the ones who are not on the waiting list, some of them are not eligible for transplants. They've had massive heart attacks or something. Some of them are just getting inadequate medical care, or the long wait deters them. They're elderly. But if there's time at the end, I'll talk a little bit about money in kidneys. Okay, so here's a graph with 2 kinds of, it's like the jellyfish. It's got 2 kinds of nodes. It's got low sensitized patients and high sensitized patients. And I've suppressed all the interconnections among low sensitized patients because it turns out it's going to be sort of a waste to match low sensitized patients to each other. They should be matched to high sensitized patients. The number of cycles of constant length is constant. So even as you let n go to infinity, you don't get more cycles of size. You don't get too many more cycles of size 3. But what you get is some really large cycle becomes probable. And again, the issue is the one I started to explain. If the probability, this is in the special case, the extreme case, the worst case of no low sensitized patients. The chance, if we can give you a kidney, the chance you can give one back is really small. But there's a good chance you can give it to someone else, that they can give it to someone else, they can give it to someone else. Eventually, when enough, when n in the cycle grows large, there's some chance it'll close. If there's a non-directed donor, then that's not a cycle, that's a chain. And we can do long non-directed chains. So that's what's going on there. When you have some low sensitized patients, then, what I showed you before was once you got to 3-way exchanges, you didn't need any more for efficiency in an ideal large graph. But that's not true at all. If you increase k from 3 to 4, or from 4 to 5, or from 5 to 6, you get a linear number of extra transplants when you have these low sensitized patients. And the reason is you can use the low sensitized patients to form chains with the high sensitized patients. So that's particularly true, if you can see it more explicitly. If you have a non-directed donor, then every non-directed donor can increase the number of transplants by a linear number. That means each non-directed donor chain could be really long. Okay? And additionally, when you increase the size of the chains, the low sensitized patients always get matched. Right? So you're not harming any low sensitized patients. The extra matches all come from high sensitized patients. And when we simulate this with clinical data, we see it pretty clearly. It doesn't hurt the low sensitized patients, it just helps the high sensitized patients. This goes back to being able to make it individually rational for hospitals. The patients who they find easy to match, we'd find easy to match too. They'd all be matched. But they would provide this big positive externality, including to the hard to match patients from the original hospital, which is that they could be matched more. So the biggest chain that Itai and I have been involved in so far was 30 transplants, 60 people. But let's talk about money now, because indeed progress is slow. As I mentioned at the beginning, I was going to tell you, I have now told you about, victory after victory in a war that we're losing. We had 40,000 patients on the waiting list when we started, and there are 90,000 now. So we're getting, we've gotten a few thousand more transplants. Kidney exchange, if it does well, could get a few thousand more a year. It's not there yet. But kidney disease is epidemic in the United States, and everyone has two kidneys. So, one question you can ask, and people don't hesitate to ask economists, why don't we just buy and sell them? And, a lot of, Gary Becker thinks that this is a no-brainer. We just have to keep explaining it, slower and more loudly, and, that's the way to go. My feeling is that, this isn't a unique thing to the United States. It's not a unique thing to kidneys. As social scientists, we need to better understand, why can't we simply buy and sell kidneys? And so let me tell you about some of the reasons that I understand. And I don't claim to know the answer to this question, why we can't do it this way. Just incidentally, keeping in my economist persona, making markets illegal doesn't stop illegal markets. I was just in Australia, so I had this slide, about how Australians are lured overseas for illegal kidney transplants. That's true of Americans too. I don't know how many, because it's hard to collect data on that. But it's hard, of course, to suppress a market when there are willing participants on both sides. Now, a problem with illegal markets, of course, is that they tend not to run very well. People don't get paid what they've been promised. They don't get the medical care they should. So there's an excellent reason to not have illegal markets in kidneys. The question is, should there be a legal market? When you start thinking about this, you notice that there are lots of markets that we don't allow. So I wrote a paper on this some years ago called Repugnance as a Constraint on Markets. And what I mean by the term repugnance is not discussed, right? There's the first sentence of the paper was why can't you eat horse meat in California? And the reason you can't eat horse meat in California is they passed a referendum, and it passed. It's the same number of people voted for that you shouldn't be able to eat horse meat as voted for Gray Davis to be governor. It was the same year. They both won. The reason you can't eat horse meat in California is not because no one wants to eat horse meat. There's no law in California against eating cockroaches, right?
I'm really concerned about it.
Yeah, but the reason there's a law against eating horse meat is because some people want to eat horse meat and other people don't want them to. Okay, so that's when I say a transaction is repugnant, I'm going to reserve it to mean that it's a transaction that some people want and other people don't want them. There are willing participants and other people who don't want them to participate in that transaction. So dwarf tossing is a good example. Lenny the Giant earns his living by taking part in competitions where he is thrown for distance. Here's the Ontario Dwarf Tossing Ban Act of 2003. It's not an occupational health and safety legislation. It says, no person shall organize a dwarf tossing event or engage in dwarf tossing. It does not say the dwarf must wear a helmet. Lenny the Giant is already wearing a helmet. It says, yuck, don't do it. A French dwarf who earned his living this way until dwarf tossing was banned in France, took his case to the United Nations Human Rights Committee. And he had a very moving statement in the case records. He said, there aren't many jobs for dwarves in France, and the essence of human dignity is having a job, and this is my job. And I thought, little guy's going to win, but France won. And France's position was that he was free riding on human dignity, that he makes all of us a little less human when he earns his living in this way, that this is, something that shouldn't be done. That translated from the French, their position was yuck. So some things are repugnant, some aren't. I would have had a model long ago if I could predict which things were repugnant, right? So jockeys are small, but there are things closer to dwarf tossing. Here's wife carrying. It's not illegal anywhere. The world champion, at BU, I gave a talk once years ago, and someone said, that's Bart Lippmann. But it isn't. But that took place that championship takes place at Sunday River Ski Resort near here. So kidney sales are illegal in the U.S., but not wife carrying, even though especially the champions who use the Estonian position, it's not that dignified. And when you're going through the water barrier. And these people, incidentally, to be clear, are not married couples. They're athletic teams, right? So it's a big person and a small person, much like dwarf tossing, right? And they're both athletes. But as is the case in dwarf tossing. Okay? So I don't know what causes repugnance, but one thing, and this gets us back to kidneys, is sometimes something isn't repugnant, but when you add money to it, it becomes repugnant. Okay? And that's the case with kidneys, right? Kidney transplants are not repugnant. Kidney exchange is not repugnant. The Charlie Norwood amendment to the National Organ Transplant Act passed without opposition. It passed by acclaim in both houses. Took 3 years, but no opposition. So it's the money that makes it repugnant, and we've seen that elsewhere. For many years, Christian churches didn't like interest on loans. They didn't mind loans. They mind interest. Adoption, it costs a lot to adopt a baby, but you can't buy the baby from the birth mother. Prostitution, we mostly object to we certainly legislate against the commercial transaction. It's not promiscuity that we're legislating against. Most people can pick the economist out in this cartoon. Poor guy is showing up for dinner saying, here's what we didn't have time to pick up wine, have $50. You wouldn't invite him to dinner again because he misunderstands what your dinner invitation meant, right? You're not a restaurant. Your dinner invitation is an expression of friendship. He could invite you back to dinner at his house. He could come with a bottle of wine that would be appreciated as an expensive bottle of wine, but he can't offer you money as a gratuity, as ingratitude for offering him dinner.
Is it clear at all that if you will allow to buy and sell, it will increase donation? Because there is some theory showing that people would do it out of altruism, but they wouldn't do it for money.
Adam Smith would say, or Gary Becker would say, you're worried about crowding out of kidneys? Crowd them all out. So Adam Smith has a line which says, you don't get your meat and your bread from the generosity of the butcher and the baker. Crowd out all that altruistic stuff and let the market supply it. Nevertheless, it's an empirical question because with kidneys, you could do that because everyone has 2 kidneys. But every cadaver that's donated not only gives kidneys, it gives hearts, and there's not going to be a market for hearts. Well, I'll ask you later whether you'd approve of one. But right? So that's a real question. It's an empirical question. It's a fair one. Let me tell you about some of the other objections. Oh, incidentally, I was just in Australia, and there are other things. These guys offered, free alcohol to women who would undress. But the reason I took it was the mayor of the town said, I thought they would have learned their lesson from the dwarf episode. So I couldn't resist. Okay, so let's see what's wrong with money. Crowding out I don't have on the list here, but crowding out is certainly one of them. The evidence is not compelling for crowding out, even with blood. That's being revisited in modern studies. But one objection, and this is sort of a religious objection, particularly in the Christian churches, is what's sometimes called commodification, and I've called here objectification. It sort of says, so 2 popes two leaders of the Catholic Church have issued encyclicals on this subject. And what they say is people are always ends and never means, and buying selling a kidney violates that, so that I don't quite know how to, to get in a discussion with that one. I mean, they just sort of say it's wrong. Now, then there are other instrumental objections. One is what's sometimes called coercion and sometimes exploitation, and this is the one that normally drives economists crazy. And it's the one that says, if you offer too much money for a kidney, you'll get people selling their kidneys who wouldn't, against their better judgment. And, the economist answer to that is, come and offer me $10 million for my house, and you can have it, even though I wasn't otherwise planning to sell it. But you could think of market design concerns or things that could address the real parts of these concerns, which are things like, people might, in desperation, do something that was ill-advised, that it might be a market with very asymmetric information, that people in desperate circumstances would make judgments that are somehow against their interests. So you could imagine, if you wanted a monetary market, you could think about a market in which only the United States government could buy kidneys. They would be allocated the way they are now, so it wouldn't be the case of rich people buying the kidneys of poor people. You could imagine there would be a 1-year waiting period where you went through medical tests and had plenty of informed consent. So I think this is something that you could engage in a market design discussion about. The third category of things I'll call slippery slope, which sort of says maybe having a market for kidneys would even be a good thing, but it might open the door to bad things. And so what you worry about in that category, I think, are supposing there was a market for kidneys, and supposing one day we suffered from a lengthy recession and unemployment benefits started to expire, and the Congress had to decide whether to extend them. You could imagine some conservative congressman getting up in the floor of the House of Representatives and saying, those poor people don't need unemployment insurance. Many of them have resources that they haven't exploited. Some of them have 2 kidneys. Maybe we would become a less generous society than we would like to be if we created this extra wealth by letting everyone sell their kidneys. So I think these are things worth considering. I don't have an easy answer to them. Let me just mention that there are lots of repugnant transactions in history and over time. Same-sex marriage is a good one because it's in transit now. It's the prototypical repugnant transaction because some people want to do it and other people don't want them to. And here in Massachusetts, you can be married to someone in the same sex, but we're litigating against the oddly named Defense of Marriage Act of the federal government, which says that in order to defend marriage, only some people can get married. Labor contracts. The most common way of buying passage across the Atlantic Ocean to North America in the days of the British colonies and shortly after was indentured servitude. You would say to a ship captain in Ireland, here's my papers of indenture, carry me across the ocean, and when you get to Boston, you can sell me to the highest bidder for 5 years, unconditional contract. We also used to have slaves. Right? That's a more complicated one because the slave is a third person. But indentured servitude is a voluntary contract entered into by willing adults. But the 13th Amendment to the Constitution says we're not going to do that anymore. Because, one way of thinking of it is in such asymmetric information markets, we decided that the abuses were so great that regulating them wouldn't be feasible. We just didn't want them anymore. So the arrow of repugnance, the arrow of time doesn't go in one direction. It's not that things that used to be repugnant are becoming less repugnant. There are some things that used to not be repugnant that are now repugnant. Some of them are in flux. So let me get a sense of the meeting. How many of you would be willing to think about implementing a carefully regulated market for live kidneys? Okay, keep your hands up. How about hearts? Okay, some hands went down, with winces in some cases. So my point there is just that many of us, even economists, have a line that we wouldn't cross. And so it behooves us to understand people whose line is in a different place than ours is. And as a market designer, I run into these things all the time. I was talking to Philadelphia Public Schools this morning. We do a lot of school choice market design. And they have ideas about what kind of information can go into allocation of school places and what can't. And you see these all over. It doesn't always rise to the level of repugnance, which it does in kidneys. In kidneys, the reason I used the word repugnance is the people who think that markets for kidneys are a bad idea think it's the kind of bad idea that only bad people have, right? They think it's a really bad idea. But in many markets, I get told, oh, that would be unprofessional or unfair or things like that. Yeah.
You didn't answer my question.
Ask again.
How many lives would be saved if we didn't have this repugnancy?
Well, there are 90,000 people presently on the waiting list. About 5,000 of them to 10,000 of them, the data are poor, die every year waiting. So certainly those, because I think, Michal's question is maybe it would crowd out and they'd be harder to get kidneys. But I suspect that we could. I suspect it. So we'd certainly save the lives of the 10,000 a year who die on the waiting list.
It seems appropriate to set that against one's feelings of repugnance.
I
Nobody ever does.
I agree. The point is some of the people who have feelings of repugnance have very strong feelings of repugnance. So perhaps they've said it against that. Incidentally, some of the people, both strongest for and strongest against, are surgeons. One of the funny things about surgeons is they don't count deaths the way you do, right? Patients die, right? They try to save them, but everyone dies. So, so their view is a little bit different. By and large, talking to surgeons, especially transplant surgeons, is very funny business for a civilian. So you have conversations with transplant surgeons where they say, oh, the patient was in desperate straits, an infant. And then by a stroke of good luck, a heart became available. And you go, oh, how lucky. So their feeling about deaths is, they're trying to practice good medicine. We could practice good medicine with people who have terminal diseases, right? Sometimes they die. You can't be a surgeon who worries, you can't be this kind of surgeon if you worry too much about people who die, because your patients die. Sometimes they die under the knife. And if that tears you up, you're not a surgeon.
I don't see what that has to do with this.
Well, you said it should be
capable of recognizing that if they watch their kids more,
of course,
fewer people will die.
Absolutely, but you sort of said, here's this big number that should be an enormous consideration. And what I'm sort of saying to you is, lots of people die all the time, especially in hospitals. For them, it might be less of an enormous consideration against the concerns they have about these things. Now, just incidentally,
so it's not very important.
Say again?
It's only 1%, so it's not very important.
Yeah. And everyone dies. So, so another question.
But then why do we need these surgeons at all?
Another question is, how many QALYs do you get? Quality adjusted life years. So you can start to play that game more, and people get different answers on that.
Okay. That's very controversial in its own right.
Exactly.
Saving those lives, that's...
Well, no, but you say saving lives, and so the question is, are you saving lives that will be lived well for a long time? Or,
We don't ask those questions.
Well...
They do in Britain, but we don't, right?
Yeah, well, so it both in Britain and here, it's against the law to buy and sell kidneys. And that's a very robust social science observation, one that we would do well to understand. Yeah?
So I think that might relate to my question, and thank you for your talk. One is, have there been studies that are cross-cultural studies in situations where hospitals are not incentivized to keep matches off their list? So in some ways, it seems like we're really focused on helping individuals solve this problem through a market strategy. But it seems like so much of the issue is that hospitals have incentives for keeping matches internal. So what about in cases where, are there cases, say, Canada or other systems where there might be less incentive for a hospital to match internally? Or are there, I can see where there would always be incentives, but in a U.S. system, there are more incentives than others.
Right. So let me go back to, let's see if I can quickly. Here we go. So first of all, so my focus is not on individual strategies in a market, but on market design strategies. That is, I would like to change the way we allocate kidneys so as to give hospitals incentive to show all their patients. Now, there's more kidney exchange in the U.S. than elsewhere, but there is kidney exchange in significant numbers in South Korea and in Holland. And in both of those places, it's essentially internal. That is, there aren't very many hospitals that you can get that surgery at. So I can't answer your question cross-culturally.
Infrastructural.
Yeah.
May I ask a related question, which is methodologically, what's important about you being in the surgery? I'd love to hear what's significant to the approaches you're taking to being so close to the exchange.
Oh, you mean that I was there? You know, they invited me to give a transplant grand rounds, and they happened to be doing one of the exchanges we had done, and they said, "Why don't you come along?" And I thought, all right. But it was very interesting. And part of it is, in a lot of market design, there are lots of details that I don't know I need to know. I don't know that there's anything particular I learned of importance there, although it impressed on me the logistical difficulties. But I find that, I mean, I do a lot of different kinds of market design, so I'm always giving advice beyond my reliable scientific knowledge, and knowing lots of details sometimes helps. So some of knowing details helps in there's lots of, I mean, sometimes it really, really helps. There's some important detail I didn't know. But it also helps in persuasion, right? Getting market designs adopted is inherently a political process. You have to get lots of interested parties to change the way they were doing something. And one of the things you discover is if you don't know something about kidneys, lots of doctors will say, "You don't know anything about kidneys, I don't need to listen to you anymore." So I know much more about kidneys than I need to do this work. Some of it's important. I told you some of it today. But I can also have a conversation that addresses some of the other concerns that doctors have so that they don't stop listening to me.
Can we maybe do one quick last question and then continue the reception?
Can the kidneys store is a strong word, but do they deteriorate really fast, or can they be put in an ice bucket for 2-3 days?
So,
because that will make the exchange.
Good question. So we now ship donor kidneys by and large. There's a long story there, but for 8 hours there's no evidence of deterioration, and for longer than 12 hours the data are very rare or sparse. So there's lots of data from deceased donor kidneys, and you've got 24 hours on a deceased donor kidney. Now, a live donor kidney is a different story because a live donor kidney starts off warm and better than a deceased donor kidney. So, but nevertheless, we used to, that picture I showed you, the donors traveled. Now the part of the free riding is donors stop traveling, and if their donor isn't traveling to you, then there's no reason your donor should travel to them. And so now all the kidneys are shipped, except when we do them in Boston among a bunch of local hospitals. So, you know, but you get 8 hours. There's no evidence that 8 hours of cold ischemia time, they call it, harms the success.
All right. Well, thank you very much.